Howdy howdy, this is Mr. Potter. In the next series of videos, we're going to actually talk more about the sorting that we alluded to in the previous couple of videos. So the question is, why do we need data sorted? And remember that we've talked about two different types of searches. We talked about the linear search, and we talked about the binary search. And when we're looking at the linear search, we always start at the first position and we work our way until we either find what we're looking for or we reach this last position and what we're looking for is not in the list. And so I can either find the spot that I'm looking for, say spot 37, that's where it happens to be, or it's not in the list at all. In the case of a binary search, wherever my data is, I start in the middle and I decide if I'm going to look in the left half or the right half. And then once I look at that half, I start at the middle and I need to decide, am I going to look in the left half or the right half? And I use this divide and conquer method, but I can only use it if my data is in order. And we remarked about how if I have 1,000 elements in my list, it's going to take me 1,000 searches using the linear search. As a worst case scenario, I'm going to go through every single element in my list. But if I have a binary search, I'm going to be capped at 11. It's only going to take me 11 chances to find what I'm looking for. So it's much more effective. The only caveat that we have is that it has to be sorted. And so what we're going to talk about in the next few videos is we're going to talk about different techniques for sorting. And the first technique that I want to talk about is the notion called a bubble sort. So I have this list of numbers, and the first thing that I notice is that these numbers are not in the right order. If I'm looking at something where I'm going from lowest to highest, I need to get these numbers in the right order. And in our previous video, we talked about the swap. In other words, the idea of how I actually go about swapping these. So if I were to swap these, then I'd have a 1 and a 3, and all the rest of the numbers would stay exactly the same. And then I'd compare these numbers, but they look good. And then I'd compare these numbers, but they're not in the right order either. I need to do the swap, and so that means that every other number is going to be the same. And I'm going to continue on. Check these numbers out, check these numbers out. Oh, these numbers don't match. So I need to swap, and everything else stays the same. And then I'm going to check these numbers. Well, they're out of order, but everything else is going to stay the same. And then I check these numbers, but they're out of order, so I need to swap, and everything else stays the same. Now, I'm not saying that this list is sorted at this point. I mean, I'm not sorted at this point. All I've done is I've just done one pass. But at the end of this one pass, I can guarantee that this number here is the biggest number because I've done a comparison, and this number is the number that got moved down to the end. Now, I can't say that this number will always be the smallest number, but I can guarantee that it will be smaller than this number because that's the process that we've gone through. So let's take a look about what's happening here in pseudocode. In pseudocode, I need to keep track of how big my list is, how the size is, because this is going to tell me how many times I need to pass through. And so I keep track of the number of passes that I'm doing. I'm starting at 0 passes, and I keep going until I get to size -1. And the reason that we have the size -1 is because if I have 12 elements in my list, the first element is 0, and it keeps going until I have list element number 11. So, and then I'm going to start the spot that I'm looking at 0, and I keep going until I'm 1 short on that. But I check to see, am I bigger than the next spot? And that's what we kept doing. I kept saying, is 3 bigger than 1? Is 3 bigger than 4? Is 4 bigger than 1? If it is, then I need to swap them. If it isn't, like it was for this streak here, then I don't swap them. So if it is bigger, then we do the swap. And then I move to the next spot, and I do that each time I go through the list. Every time I go through the list, I only get one number guaranteed. So the second time I go through the list, this number would be the next biggest number. The third time I go through the list, this would be the next biggest number, and so forth. So I have to go through and make a number of passes equal to the size of my list -1. So, real quick recap about the swap. Remember, the idea behind the swap is that if I wanted to change this 4 and this 3, I had to come up with a temporary spot. so that I can say, okay, I want to take this 4 and put it here in the temporary spot. And then I can eliminate this 4, replacing it with the 3. And then I can eliminate this spot here and make it with the 4. So I've got this idea that I have to come up with a temporary memory location to hold the number while I'm actually changing the places. Because otherwise, if all I have is a 3 and a, excuse me, horrible. If all I have is a 4 and a 3 and I want to copy this number over here and I make that a 3, now I have no idea what the number used to be. That's why we need this temporary spot. So, I want to go through and I actually want to take a look at this. Now, I will warn you that this is probably the slowest sort that we're going to talk about, but the process is the easiest to understand. I look at numbers, and if they're not in the right order, I swap them. So these are going to be swapped to a 1 and a 3. The 3 and the 4 are fine. The 4 and the 1 are not, so they're going to get swapped. 4 and 5 are fine. 5 and 9 are fine. 9 and 2 are not, so they're going to swap. That means this is now a 9. 9 and 6 are not. 9 and 5 are not. And my 9 ends up being over here. And this is known to be in the right spot. I do it again. 1 and 3 are okay. 3 and 1, not so okay. Swap. This is now a 3, so 3 and 4. 4 and 5. 5 and 2, that's not right, so we swap. This is now a 5. 5 and 6 is okay. 6 and 5, not so okay. So I need to swap. That means this is the 6, and I don't even need to look at this 9 because I know the 9 is correct. It's my known good spot. But because I've gone through 2 passes, I now know that 2 of these numbers are in the right spot. And if you look at this list is almost in order. There's just a little bit right here that's a problem. If I go through the 3rd pass, that's okay. 1 and 3, 3 and 4. 4 and 2, that's not okay. They're going to have to swap. So this becomes the 2, and this is the 4. 4 and 5, 5 and 5. And now I've got 3 numbers that are in order, 5, 6, and 9. I do this process again. 1 and 1, 1 and 3, 3 and 2, nope. 3 and 4, 4 and 5. And now I have 4 numbers. And this is something else that we have to be careful about. Even though at this point the list is sorted, keep in mind that we are only on pass 4. So the thing is, we have no idea if we're done or not. We have to go through the process. We have to do the comparisons because we need to get down to where we have pass 0, 1, 2, 3, 4, 5, 6, 7, 8. I have to go through pass 8 and make sure that this works out okay. But what I'll find is on pass 5, this one's okay. On pass 6, that's okay. On pass 7, that's okay. And on pass 8, this is okay. Well, if these numbers are all in the right spot and I only have one number left, this number here has to be in the right spot as well. Now, this process of just doing a comparison and comparing pairwise, piece by piece as we go through the list, is slow. And the fact that I don't know the list is sorted until I actually go through all 8 passes, that's slow as well. And so the question then arises, what are we looking at when we're looking at a best case or a worst case? Keep in mind that if I look at the code for the swap, I had to have my temp, and then I had to have list sub spot, and I had to have list sub spot plus 1. So in other words, whenever I had to do a swap, I had to do 3 extra lines of code. And that really helps us to determine what our best case and what our worst case is. An ideal situation would be kind of like what happened after spot 4, where the list is sorted. I'm just comparing these values. I don't have to physically swap. And if I can go through without having to physically swap, it's going to go quicker because that's 3 less steps of code that we have to do each pass. So my best case scenario is when the list is already sorted because we have fewer swaps. So that means that my worst case scenario would have to be a situation where I have to do as many swaps as possible. And that's going to happen whenever I have something like this, where my numbers are actually in reverse order. In a case like this, I'm going to compare, swap, compare, swap, compare, swap, compare, swap. and the 9 gets put over here. Notice I was comparing 9 with 8, and when I swapped, I was comparing 9 with 7. I swapped and compared 9 with 6. I swapped and compared 9 with 5. This number is now in order, but look at these other digits. They're still in reverse order. So I compare 8 with 7? No. I compare 8 with 6? No. I compare 8 with 5? No. I compare 8, well, this is the spot here because I know 9 is good. So that means that 8 and 9 both have to be good, and so forth. So my worst case is when I'm actually in reverse order. So that's something that I have to keep in mind, is that the code is actually going to run slower if there's more work to be done. Of course, that makes sense when I say it like that. But the question is, what do I mean when there's more work to be done? I mean that there's more of these swaps to be done. Every time I have to do a swap, that adds 3 lines of code that has to be processed. And every time I do a list like this, there could be 5 times 5 or 25 possibilities, 25 comparisons. So that means that I could have 75 additional lines of code depending on if the list was already in order or if the list was in this reversed order. So that's how we deal with this idea of a best case versus worst case. One thing you do need to know is that although this sorting technique is probably one of the easiest ones to implement, one of the easiest ones to understand, it's actually one of the slowest sorts that we're going to talk about in this course. So in the next couple of videos, we'll actually talk about 2 sorting techniques that are slightly faster. And by slightly, I mean that they still operate on the idea of n squared time, where if I have 5 elements here, I had to do 25 comparisons. If I had 10 elements in this list, I'd have to do 100 comparisons. All of these lists run on this idea of n squared time, but how they do their algorithm is what actually makes them more efficient. There's going to be fewer comparisons, fewer of these times where we're going to have to add this 3 lines of code. And so there's going to be fewer times where this thing is going to bog down. So that's where we're headed for in the next couple of videos. So once again, this is Mr. Potter. Thank you for watching. Have a great day.